Thank you very much. And I really appreciate you coming back, even though I don't have electrochemistry keyword in my title. I guarantee you I will link that. I will link that to show how this can set as a stepping stone for the next step. And actually, electrochemistry is very important for the actinide, as I will show in the next couple of slides. Okay. I've been asked this question a couple times, so I would like to share a little. Where is Los Alamos? Here is Los Angeles, only about 13 hours driving from Los Alamos here. We're in the middle of nowhere, but we do have a beautiful landscape. So this, looking. So if you go there, and I know there are a lot of avid hiker here. If you go there, you're gonna really enjoy it. Okay. Los Alamos is very large. We have it's a large laboratory. We have over 17,000 staff members, and then a lot of budget and the land, working on quite a few areas, particularly on chemistry, materials, and theory. That's very relevant to this workshop. What you see, this arrow is where theoretical division. This is where Seaborg Institute that I'm associated with. If you go there, you're going to see superstars, not only superstars in terms of science, but also in the real sense, movie stars. I hope any of you have watched this Oppenheimer movie in the last couple of years. Awesome. So in addition to the lively discussion we had today regarding those transition metals, we're going to switch gear a little to the bottom of periodic table. What I proudly say, actinides serve as a foundation of periodic table, right? We are the lowest layer here. There are some really important applications for these elements. This is space exploration, we need plutonium. And the nuclear energy, of course, need all these elements. And this national security related applications is very important for those elements. For all those elements, there's a key implication is after this nuclear fuel being used, we call the spent nuclear fuel, how to store this, how to deal with those nuclear energy fuel is very important right now. So in the past, people consider, and even now, is this deep geology burial. Essentially, you dig a very deep hole, like 1,000 feet deep. You bury this high-level radioactive materials down below for thousands of years or even million years until they decay out. As long as in the deep, you have water. So this, I think, really tied to the discussion here is this chemistry where the water get in touch with all those nuclear fuel and what's going to happen. Of course, beyond those natural redox reaction, it also caused by the radiation of those materials. So you can have different type of reactive material speciation generated and that cause more reactive interaction with these nuclear materials. Instead, we have a very shiny ring of plutonium or uranium. You notice they cannot be shiny too long in the air. So with plutonium, you'll see like in 2 days, you will see those materials just naturally pop off with millibar of the oxygen. So very low oxygen, super reactive materials. With pure uranium in the 1 hour in the air, that's what you see that's being oxidized to oxides. So that's this very reactive materials. So here is this material look like. If you see this uranium, this is the uranium fuel that are being prepared for nuclear reactor. It's in reasonable shape, but this is irradiated uranium fuel. This is when you take this out of a nuclear reactor, it almost becomes porous. So a lot of surface defects, a lot of chemical reactivity associated with that. This material is very complicated, like you can see here. All sorts of different oxidation state, different form of phase, because of the chemical composition between uranium and oxygen is very complicated. Okay, same likewise for this uranium with water, just the per Bay diagram is also very light as well, very complicated as well. So because of this complexity of those systems and then the difficulty to study materials, I have to say this field for actinide at the interface is really lagging behind compared to the platinum, for example, here. So we have a lot to learn, a lot of methodology developed in this workshop going to be really helpful for us to study those chemistry. So in my talk, I'm going to mention the water absorption of actinide at this interface, what's their speciation, what's the surface reactivity caused by defects. As you see, defect is inherent for those materials. And what chemical conversion can be induced by this type of defects. And then in the last couple of years, we've been thinking, how can we help reduce this corrosion? So what can be used as a surface coating for those materials? And then at the end, I'm tied all those surface reactivity to this electrochemistry of actinide material. Okay, no surprising, even as a complex system, DFT is the workhorse for those fields. So what you see here, I highlight using thorium and uranium because these are the two most reactive materials. Pretty much if you use PBE plus U, right? So you have to choose the right U, you can get the right band gap. So we can reproduce the bulk property reasonably well. So here is highlighting the lattice constant of thorium. The band gap of thorium is wider, so it's less sensitive. Uranium is more sensitive, so to the U, for this one, we can get reasonably well reproduced. And then the formation energy is also reasonable. That kind of provides some foundation we can move forward with this method. So since we're talking about the surface energy, so one thing is that we want to know which surface is more stable. Experimentally, pretty much you observe this 111 surface. What's the energy you see here are the formation energy of those surfaces, which means that the lower energy should give you this more stable configuration, more stable surfaces. So this is also experimentally observed as well, and you can see they are also most stable for the oxide. Pretty consistent. So in order to study those calculations so far, there are different levels of theory. One thing here is trying to see the surface absorption for the water on this different type of surfaces. One thing we have to make sure, like Mira highlighted in this proton, this hydrogen and the platinum surface, we also need to do configuration search for those systems to ensure we get the right minimum. And then for the water as well. The only complexity here we have is once you have water absorbed to the surface, they can have two different types of format. The type pattern, one is molecular, right? So you stay as water, but actually you can also easily dissociate. So you have the oxygen of the water that tied to the actinide in the surface, and the other proton transfer to the other oxygen in the lattice. So this is a dissociative state. And in fact, for those perfect surface or pristine surface, you notice that this molecular absorption versus dissociative absorption pretty much comparable. The dissociative is slightly more stable, but you will observe both status, both pattern in the interface. And this is the same, this is particularly for the most stable surface, but for this higher energy surface, actually dissociative is much more stable. So what you see here, pretty much we will see dissociative absorption. And in fact, if you have surface defect, this surface dissociative energy will be much more higher. So you end up with dissociative absorption a lot. And one thing is on this actinide system, particularly once you go beyond the thorium, you have uranium. So the uranium oxide here is uranium in oxidation state 4. That means you have 2 F electrons, 2 unpaired electrons in the uranium. So you have the spin up, spin down. And when you have this different magnetic coupling, trying to identify the lowest ground state of those systems, we need to consider all of this. But the conclusion is once you have perfect structure, there's a spin up, spin down, they need to antiferromagnetically coupled, and then they will confirm with the experimental results. As I mentioned, all those are radioactive materials, so you can have this radiation decay and generate a lot of defects. And the one particularly reactive will be the surface defects you see here. So since oxygen is much lighter compared to uranium, so if you have radiation, you kick things out. Oxygen atom is much easier to be kicked out, so leaving the oxygen defects. And then often the time these defects, you leave the oxygen carry 2 minus electrons, right? 2 electrons. So you kick the atom out, but then you leave the electron behind. So this is a typical surface defects. So with this surface defects, it's actually because of those special electronic states of these F elements, you will see different surface electronic structure. So for example, for thorium system, if I kick out this oxygen atom, this ground state surface, these 2 electrons are not moving anywhere. They stay at the vacancy side. And that's very unique. Some electrons stay in this vacancy side, there's no electron support, no atom supporting it. But actually, if you're as a chemist, you know this is also electrolyte, right? So essentially, you have those 2 electrons staying here, are ready to react with any molecule coming in the site. And this is not only for the surface, but also for the defects in the subsurface as well. So now we're moving down the series. That is, go to uranium. So once we move down series, the F orbital is being stabilized a bit more. So now you change the structure. So those 2 electrons, instead of staying at the vacancy side, one of them moved to the metal. So it's being reduced to the metal side. And a similar case for the surface and the subsurface as well. So if you move to plutonium, actually, plutonium is the most boring system here, even though it's critical materials in other sense. So that's because of this surface, the redox potential for plutonium between 3 and 4 is lower than those, so than uranium, thorium. So ending up that both electrons just moving to the separate plutonium. So they are less reactive. So this is consistent with what you see, what we call periodicity for the actinide series. Once we move from from the beginning of a series, actinide, to the Lorentzian, the last element, what you see here, this d orbital relatively stable. This usually is unoccupied. But F orbital keep dropping. Once it keep dropping, basically more stabilized, so the redox potential, they basically take less energy to deposit the electron in those orbitals, so they are, the F orbital are more electron more localized. And this also coincides with this smaller radius, right? So because you go down the series, this radius is getting more shrinked, and that means these more electrons are more trapped. So that's what you see in terms of chemistry is after plutonium pretty much starting with americium, this electrochemistry for the later actinides are pretty stable, very similar to lanthanide, like lanthanide 3. So the exciting chemistry line up for the early actinide system. As I mentioned that these electrons can behave very differently. They can be delocalized or localized. So to describe the right ground states of those systems is very tricky. And actually, there's very nice work done by Vandele Valley in 10 years, 15 years ago. So they demonstrated that for this highly correlated system, actually, by the way, this is actually done on uranium oxide. If we just directly do single point calculation or optimization with DFT plus U, often you end up with this metastable state. That means this electron can localize, can move around, and you can get a lot of metastable higher energy than this global minimum, than this ground state. And this is because of this DFT plus U didn't, it's very hard to capture this. So in this correlated system, in the molecular system, you can do multi-reference calculation, which we often do, but for solid states, you just don't have such a tool available. So what they develop is they call the U-ramping method. And this is really critical. So the idea is that you're starting with pure GGA with no U, and then you have very small incrementation of this U with like a small step, 0.1 eV, for example. And then you get that converge, and the next step, get another increase this U value and get that converged. So eventually get to wrap up to the U value your target, give you your targeted bandwidth, for example, 4. So that means for one single DFT plus U calculation, if you have a small step size for this U value, we need to do 40 calculations. And in order to get this ground state. So you can see this calculation is much more complicated in terms you are trying to get the right accuracy for those systems. And so with all those considerations, so now we understand we have confidence about our ground state of those surface charge and surface reactivity. So now we put in water into those reactive materials. So you put in water, remember, on the pristine surface, they can stay as both dissociative or molecular. They can have the mixture of both. But now we have a surface defect we're putting water on, and actually it end up immediate reaction. That means this 2 electron at the vacancy site reduce the water, form hydride, and you have the OH as a group on the associated with the coordinated with the thorium. And this reaction is pretty much barrierless. Here is I want to show this number is really the upper bound, right? Because we didn't consider the whole reaction. We didn't have other water molecule to facilitate this reaction. We basically only have one water molecule. So that's where you can do the AEB calculation, get estimate this number. But this number barrier is overestimated. But even this upper bound tells us this number is very low. So now this being hydride, we know hydride is H- is very reactive. So now that one can grab this hydrogen and release gas. So if even I put one water molecule, I can get a hydrogen gas out of this. And this reaction barrier is about 0.4 eV. So now, moving on down series for the uranium system, similar, like I say, you have one electron here, and this one electron can be also reducing. And then we add in water here, that's a similar thing happen, right? It reduces this hydrogen, and then eventually you can release this hydrogen gas. But since you only have one electron instead of 2 electrons, so this reaction release this is a much higher barrier in this case. Again, once we have more water, actually, if you do AIMD calculation with more water facility, this will be significantly reduced, this barrier. So putting all those together, you see this comparison from thorium. We set the initial structure as 0. And then you see this energy barrier overall is a downhill reaction. So it's a thermodynamically stable, even to release the hydrogen molecule. And then this thorium is particularly reactive compared to uranium and plutonium. So to summarize here is once we have this water splitting reaction on this interface, if we have pristine surface, we have this happen. In order to have this reaction happen, you need to inject a lot of energy to break this bond. So this is thermodynamically uphill, it's prohibitive. But once you have surface defects, And here, with this availability of those electrons, this reaction moving spontaneously. And that kind of gave us a lot of idea, if you think, how can we use this special electron state to help us to convert some very inert chemistry that's very difficult to do in general. Oh, before I move on, actually, we really want to see this experiment validation. So this is a really neat experiment. So what you see here, they done actually, way before we did our calculation. They have a stoichiometric, if you think of the pristine surface of uranium oxide. And then they put water inside and do, in this chamber, and do this temperature programmed desorption. Once you have pristine surface, you do not observe any of those peaks. And this peak is what they measured is a hydrogen gas. Okay, so they have a gas detector and they collect all of them. And then you see this number here, this time. That means it's a time they bombarded the surface with argon. So if I bombard the surface with argon for 50 minutes compared to 50, that means you have more surface defects in this 50. And that's where you observe more hydrogen gas. So that's kind of a direct measure, validation of our theory calculation to show once you have surface defects, you can have this reaction happen spontaneously. So this kind of reaction can be really diversified because you see here is what I'm showing some early work when actinide materials has not been demonized. Actually, people notice those kind of special reactivity of actinides, and they have used a lot for the surface catalysis. What you see here is this catalytic oxidation of carbon monoxide. When they compare this with the common catalysis, for example, vanadium oxide, tungsten oxide, and this thorium oxide and this uranium oxide is much more reactive compared to the rest. And this is done in 70s. And at the time, people try to solve this issue, right? Because you have a lot of volatile organic molecules, particularly those molecules have this chlorus system on it. They are very toxic, but it's very difficult to decompose them. In order to get rid of them, people need to find those catalysts that burn them at a very high temperature. What you see here with the cobalt is a very typical catalyst. You need to have higher energy with a conversion rate only about 60%. But in fact, if you use uranium oxide, this conversion rate, the temperature much lower, conversion rate is much higher, and including higher selectivity as well. So even in the recent years, there is a more revived study on this system. So this is the catalyst with two different metal centers, both cobalt and thorium, cobalt uranium. And what you see here, this front line is this cobalt thorium here. So basically, this is really important, given the higher catalytic activity when you have actinide in the system. And this is for the CO2 to methane conversion. So we're kind of really interested because you have all those electrons at the interface. They are ready to react with any molecule come closer. So one thing come to mind is this very, I think everybody here knows this nitrogen molecule is one of the most stable chemically inert molecule. So with this, once it gets in touch with this surface, it will immediately absorb those two electrons. So now you break the most stable triple bond to double bond. And then the rest of this chemical reaction happens just readily. So it's very easy to go downhill reaction. The energy released here can catalyze the last step of the release of this gas. So this is so far it's a theoretical prediction using DFT. Apologize for the meeting here. And that can happen on both. So even now, people doing this, they usually use a bimetal center. Essentially, one metal center reduce or activate nitrogen. The other metal center activate this hydrogen. But once you put in actually using actinide, you can activate both molecules at the same time. So you can make this manufacture or design of those catalysts much easier. And then this is the reaction mechanism. Here is what I want to point out is that for the uranium system, you have two different types of uranium, right? We said one electron at the site, the vacancy site, one electron at the uranium center, and this is play a role at different steps. The first step is this electron reduce nitrogen, and then the second step, this electron will bind, this uranium will bind this center again. So reactive the nitrogen, hydrogen, and then now you release that. So upon this release of this ammonium, this phase is coming back. So basically there's a way, or if you think you generate surface defects pretty easy, you can just bombard it. So you can regenerate those catalysts easily. And then I will not go to detail about another reactivity, but just try to highlight for even more complex system with this carbon monoxide, So what you see here is that you can also activate this reaction through hydrogen or CO activation as well. So this is kind of shows the diverse application of those surface reactivity. And that's kind of what we've been trying to understand in the last couple of years. And then in the lab, instead, I think there's one thing people always wondering, would you really use actinides as a catalyst? Right, they are radioactive. Is this something you're serious about it? But in fact, if you think the radiation reactivity, they are really low for the depleted uranium. Because once you concentrate them for the nuclear fuel, the depleted uranium is very comparable to your banana. I mean, banana, you have higher radioactivity because of potassium-40, and actually this depleted one is comparable. So it's a very banana in a real sense. Okay. So that means that now, if you really think that you concentrated this uranium-235 for the nuclear fuel, but then the rest are really useless. It's being piled there for, we don't know what to do with that. So if there's a way we can recycle this for catalysts, that would be really good. So in meanwhile, we want to say, is there any way we can help protect those materials? And then what we want to find is some surface materials that can keep all those toxic molecules out, because like a nuclear fuel you manufacture, usually you don't use right away. You can be sitting there for a couple of years. You want to make sure it's not corroded before you use it, like those situations, right? So one idea we had is actually inspired by the photocathode people. They want to have some system protect their metal cathodes, but in the same time, you can have electron and the heat coming in and out easily, but you don't want to have chemicals there, so we want to use 2D materials. We're kind of really interested to see if this can be used for actinide system. And in order to design this, we need to have this coating system that is chemically inert, right? You don't want them to react with oxygen or CO2. And they need to be thermodynamically stable. They cannot decay by themselves, and then also highly impermeable for those other gases and the small molecules. So after sift through those database of 2D materials, we pick up those couple categories to study. The first category is a very stable graphene family. If you think it's a graphene or boron nitride, these are insulator. And then you have this transition metal, dichromide. And then they have this MO, right? Molybdenum disulfide and molybdenum diselenide. And then they consider as a semiconductor as well. And then you have this very special category MXene. Even though this is a pretty new category, and then people haven't thought about that, but we're really impressed by the performance of those systems overall. Okay, I think I might finish early. So this one, what shows the binding constant here, right? So we want to know how those 2D materials bind to the surface. For this graphene family here, you see the pretty low energy, less than 1 eV per unit per uranium atom, which is unified for those systems. Because you have a different size, you cannot use the same lattice because you want, if it's the same lattice, then you need to match the 2D materials with this so you don't have too much surface strain of those systems. So this need to be adaptive. But in order to be comparable cross system, so we normalize to per uranium atom on the surface. So now you see this energy pretty low in general. So graphene is higher than boron nitride. Pretty much you can see boron nitride is a physical absorption. So there's not much interaction for those systems. But then for this transition metal, this TDM system, they are getting much stronger. But the most strongest one is this MXene system, close to 3 eV. So for what? What are the reasons for those systems? So if you compare that, these are the physical absorption for the graphene family. So basically, you have a van der Waals interaction, absorber on the interface, and they stay there, but they're not much stable. For this TMD system, if we characterize that, there are some, so if you see here, there's a yellow color, means that there are electron density accumulation between those interface. So this is considered as a chemical absorption because they are much stronger than the physical absorption. But for this MXene system, they actually really interesting. They form a real chemical bond with the surface. And that's why they are so strong. So this is quite interesting. So what we did for those systems is the uranium metal. We're just trying to do a proof of concept for the first step. And then the next step is we want to see if we have surface corrosion, because you know there are no pure metal. There are always oxides interface, whether that will happen as well. So here is the, if you integrate all those charge density in the previous slide here, and then you will see how much of electron density accumulated. And then we see for this MXene, it's much stronger compared to the graphene and the boron nitride. These are the really small perturbation of electron density. So what you see here is a positive value. On the right side is accumulation, or really, if you think there's a polarization, and here is a chemical bond. It's getting much stronger. So I mentioned that we really want to know that absorption work for the metal center and metal surface, but whether they will, if you have oxygen and the interface, right? Any of metal you have oxide on this particular uranium, plutonium, then as a result, whether this repulsive oxygen actually can reduce, whether it will make those 2D coating not working. So here we consider both as both oxidized surface compared to the pristine versus reduced surface. By removing oxygen, you have more electron. So in this case, we consider the whole suite of 2D materials and compare them. As a result, you see here, we combined everything together. From this this blue bar on the right is the pure metal. And on the left is from pristine oxidized reduced surface. And you can see there's some variability at the absolute binding energy. But overall, they are very strong for this mixing. Still stay at the same category. But these two, like this transition metal, dichromide, they reduce significantly for oxides. But for the metal, they have a higher dipole interaction. So this kind of make this is still very strong and very valid. So far, this is a theoretical prediction. I think we have some colleagues interested to synthesize, validate them. Let's see, someday they're gonna happen. So this is the charge density rate distribution after the coating. What you see here is really to show you what you see from the left to the right. You have much more blend of the charge redistribution. So the yellow color means accumulation, gray means depletion. So there are a lot of mixing, redistribution, and make this bond much more chemically stable. Actually, if you think for the mixing, you can do a lot of surface decoration and modification. And if this is chemically stable, this will be a really good coating system for this actinide materials. I promised I would tie this surface chemistry to the electrochemistry to this workshop, because in this field right now, I think you notice those references are very recent. So for this spent nuclear field, people realize there are a lot of energy inside. If I let you guess, for the spent nuclear field, how much energy we have been used? We actually only use 5%. So there's still 95% of energy in the spent nuclear field. So in US, they only did this once through cycle. That means they don't want to deal with this waste and this risk management, particularly for plutonium. So then basically after 5%, and you have the fracture, you will notice the structure change a lot, and you have a lot of fission elements like lanthanum, like build up. So then now this efficiency reduced quite a lot. So they just trying to bury it. But now at the age of energy crisis, I think we all realize actually just throw it away is not the smartest thing. So there is a big push trying to recycle those nuclear energy. And then there's different ways to recycle this. For example, one thing is you can dissolve them and do the separation. That's which another project we've been working on to design ligand to separate them. But there also another way is this electrorefining. So you can put in this spent nuclear field directly here, trying to dissolve them using molten salt. So here is a little bit different because you cannot have water there, but you have this molten salt, and now they can facilitate, you can reduce to pure uranium, or you can throw the rest of this minor actinides and the uranium plutonium with a different cathode. So this is experimental result to prove a concept, but actually theoretical understanding, I would say not even started yet. So there are a lot of work that can be done. A lot of technique in this workshop can be applied to there. Likewise, in order to support nuclear energy, you need raw materials. So where you get this uranium? There's one thing is talking about extraction of uranium from seawater. You have to see in the past, most work is done by absorption, right? They design different polymers, different type of MOF with a different functional group to absorb uranyl, this one, from the seawater. But it's very dilute. And then pretty much your system can saturate really quick. So the driving force is not there. So I'm excited when I search for this. It's a very recent work. They actually trying to use electrochemistry. So essentially anything absorbed there, I try to convert them right away. So you always have constant potential. So this seems pretty promising. As a way is that you have the uranium oxide at the interface, and there's a conversion from this different chemical form of uranium to be concentrated as a solid. So this is a kind of I think right now, as a standing of the field, people are starting to understand the surface chemistry. But if I use the language of this electrochemistry field, is zero potential, right? So we have no potential. We just trying to understand surface defects. But they are very important to let us understand what methodology we should use in order to understand the more complicated chemistry here. So here is this our conclusion, basically, based on this type of work. So surface defects is very important. And in order to characterize those surface defects, to get the right electronic structure, magnetic property, you really need to be careful about what method you use, how do you use in order to get the right energetics. Because for one configuration with 0.5 eV, it's probably too much of uncertainty to draw any conclusion. And then the stability of these defects are different depending on what actinides you use for your base materials. That's because of the redox potential from thorium to uranium to plutonium are very different. They stabilize F electrons, so this change the redox potential for those systems. And then I think the defects really increase the surface reactivity. You can see there are a couple of catalytic reactions. It can active nitrogen, CO and CO2, and a lot of chemical reaction can be used. And then last, we just try to see, at least so far, theoretically prove that the viability of using 2D materials as a surface protection layer, and then that is ready for the validation. Here is, I really want to thank the team over the years, postdoc student who did the calculation, and my long-term collaborator, and also as well as the funding resources through BES and the Lano Institute. And most of all, thank you all for your attention.